go back to that one. So I'm going to talk a little about using artificial intelligence to like find new archaeological sites and such things. And there has been quite a lot of activity in this field during the something like the last 10 years. So there has been a huge boom in archaeology in research related to using artificial intelligence to, like, for example, find new archaeological sites, and in using different kinds of remote sensing data to do this kind of research. And there are a couple of good reasons why this is so. So one is, of course, that it's actually a really nice machine learning problem to like try to use artificial intelligence for this kind of stuff. So people think it's cool, and it's actually quite fun to do that. So that's why people have put quite a lot of effort to develop different approaches to this. And also what it tells us is that the technology is now sufficiently matured so that there are like good approaches to doing this kind of stuff. So you don't have to like start from scratch and like do all by yourself. So there is like established solutions for different kinds of tasks. And also all of this kind of relies on the fact that there is like sufficient data sets that we can use to train the models, and also that there is like good enough remote sensing data that we can like use that data to like spot new archaeological sites. And nowadays there are, for example, in Europe, many countries have their own national laser scanning programs that are producing huge amounts of really good remote sensing data. So we kind of have all the necessary pieces in place now, so that we can start to apply these kind of things in scale. And that's what I'm going to talk about today. So, and the focus is more like not in the actual like machine learning process itself, but more in like how do we make efficient use of the results in heritage management context, so that how can we actually apply the results in practice. And as I kind of realized that there are non-archaeologists in place, so many of the things might sound a bit foreign. So first, I'll just quickly introduce the kind of remote sensing data that we rely on in this kind of research. And that's mostly airborne laser scanning data that many archaeologists are familiar with. And the basic idea is that we take a laser scanner, fix that into some kind of airplane or other aerial platform, and then just scan the landscape. And what this produces is a kind of point cloud, which like is a huge collection of like three-dimensional points that are measured. And this can be used to do a wide range of different things. And in archaeology, it's mostly used for like topographic data, so that it can like show local topography in great detail. And this can be used, for example, like in traditional archaeological surveys. People can use it to like find different features that point to presence of archaeological sites. And also it's widely used in heritage management sector and research. So for example, archaeologists working in heritage management might like make their assessments of if there is like likely to be archaeological heritage in a certain area based on this kind of data. And in Finland, we have a few like national airborne laser scanning datasets available to us. So there is the like first national dataset that is now a bit dated from 2008 to 2019. They did a laser scanning program with a relatively low point density. And this was already widely used in archaeology, but it didn't really allow us to do anything in precision, so that only few archaeological sites were actually visible in that dataset. So it was mostly useful for like topographic analysis. And then in 2020, they started a new laser scanning program with much higher point density. So now it's like 5 laser pulses per square meter. And this is enough to show most archaeological sites that are visible above ground, so that they have actually some kind of visible characteristics, such as like if you imagine a grave mound or something, so that there is actually a visible mound. So it should be visible in that dataset. And then we are going to have a new laser scanning program starting in a couple of years, but we don't really have any specifics about that. And to just give a quick overview of how this like AI assisted detection of archaeological features work. It's actually a really basic machine learning approach. So first you have to like prepare some kind of training data, just such as like digitize known archaeological features, and then feed those to the model, train it to find similar things, and then apply the model to some other dataset and start finding new stuff. And there are different machine learning techniques for doing this stuff, such as the ones listed in the slides. And well, for the purposes of this presentation, we kind of just assume that all of those work. Under the hood, they do slightly different things, but they can be used to achieve similar goals. So it's not really that important now. And for any of this to actually work, it also kind of requires a couple of things from the archaeological sites we are trying to find. So they have to be present in sufficiently large numbers so that we can have enough training data. So if we have some archaeological sites that we only know 10 examples of, that's not going to work. So we need at least hundreds, preferably more. So it's more is always better. And then they should also be visible in the remote sensing data we are using. So it makes no point to trying to use this kind of stuff to find things that are not visible in the data we have. And just to give you some examples of archaeological sites for which like this kind of approach is useful, we have tried this with pitfall traps, which are like hunting pits used to catch like different kinds of deer, elk, and so on. And these are usually visible in the landscape as small pits. So really simple features, but they're usually identifiable in the laser scanning data. And they're quite easy to recognize, especially if they're present in these kind of long chains of pits. So that helps to like distinguish them from just whatever pits. And then we also have tar kilns and charcoal kilns, which are really common type of archaeological feature. And these are slightly more complex in the LiDAR data. So these are kind of easier to identify just by the visible signs. And also they are present in really large numbers. So those are ideal for this kind of research. And then we have other kinds of archaeological features that are also possible, such as like remains of Stone Age houses that might be visible in the landscape as like shallow pits or depressions. And these are actually quite difficult to find using this kind of approach, but archaeologists think that they're interesting enough so that they are ready to accept slightly poorer results and just put more effort in verifying those. Yeah. Okay, and most of the experiences here in this presentation are based on an old proud project of ours. So we did this small pilot project in AI-assisted feature detection a couple of years ago, together with University of Oulu. And for the more technically minded people here, we decided to use a model based on UNet architecture. So we are making pixel-based semantic segmentation and not like traditional feature detection, but it does the same thing as the other approaches, so it doesn't matter that much. And we use this approach to map archaeological features based on the national LiDAR dataset from the National Land Survey. And from the very start, we tried to make this happen in a really large scale. So even our pilot project actually managed to analyze about 100,000 square kilometers of LiDAR data. And here are like just a quick overview of what we actually did. So we managed to use this kind of approach to detect a lot of archaeological features, mostly tar kilns, because those were the easiest. But we also did some work with hunting pits and other kinds of archaeological features. And we did got like pretty good results. So we learned that it's quite efficient, so that we, with very little effort, we can find a lot of stuff. And that the data we can produce was pretty good. So the main benefit here was that we managed to produce data with really precise coordinates and spatial information. With traditional archaeological surveys, where the coordinates are often based on GPS devices, it's actually difficult to match that kind of precision one can achieve with the help of the LiDAR data. And we also learned that it can produce pretty reliable results. It's not always true, but in optimal cases, it actually does pretty well, and we can actually produce useful data. But the thing that actually turned out to be really difficult and tricky was to actually make use of that information in heritage management context. So we have all these kind of questions about how we should integrate this into the existing databases and workflows we have that are very much based on traditional archaeological fieldwork. And also, we didn't really have any strict requirements or idea what kind of data we have to want to actually integrate in our system. So we have to come up with new guidelines about that. Also, we quickly realized that we don't really have the processes or guidelines for managing this kind of research. So it often happens outside the kind of established heritage management processes, and it can be tricky. And this is actually a flip side of it being really efficient. It kind of also forces us to think about our own priorities and administrative workload in the different light. So that if we suddenly can find a lot of stuff, we also have to kind of think how we are able to manage those sites in the future. And the rest of the presentation is really devoted to our current answers to these challenges. And this is still very much a work in progress. So this is mostly a collection of things that we have already decided to do, some things that we are planning to do, and some things we don't really know the answers for at this point. And one of the very first things we recognized as really important was to build the competence in heritage management sector. And there, the kind of key players we have to look at are our own kind of regional museums that actually have all the tasks where this kind of data and results are really important. And those are the kind of things like taking archaeological heritage into account in urban planning, forestry-related things, land use, and that kind of thing. And all of that happens in 23 regional museums across Finland. And these are really diverse group of organizations. So some of them might only have one archaeologist that has to be able to cope with this kind of new data. And some of them are bigger organizations that actually have some capabilities themselves to do different kinds of stuff. And in the Finnish Heritage Agency, we have tried to systematically build the competence in these organizations so that they can, when we start throwing this kind of information on them, they actually know how they can like independently assess what they should do about that. And we've had many like workshops and clinics focused on like developing competence in how people can use LiDAR data independently and like processing LiDAR data for their own use, and also how they can efficiently use existing GIS tools. Then that stands for Geographic Information Systems. So we, for example, we've offered some assist in using QGIS in heritage management. And one of the key challenges here, which we are facing, is that the LiDAR data set we are having, it's actually use restricted. So each of the museums here, they have to kind of have their own means to use that data efficiently. And that's a problem we can't really, for example, we as a heritage agency can't like just directly provide ready processed LiDAR data to those museums. They have to be able to do it by themselves, but we can offer like assistance in doing that. And that's one of the trickier challenges we are facing. The next question is that what kind of information we want to have in our national databases and systems. And the question is really about like how reliable the data has to be. For the heritage management officials in those regional museums, their worst fear is that we are starting to like integrating huge amounts of AI generated data that isn't very reliable, and they have to like clean up afterwards and like clean up the mess. So we have to be quite strict that there are certain like criteria of like what's reliable enough so that we can start to like integrate that into the database. But from the very start, we have decided that we like want to have all those like newly identified features as part of our national fornminnesregistret. You have something similar in Sweden, so it might be easier to relate to that. And before we can do that, there are a couple of questions we have to answer. And first one is that are the newly identified archaeological sites automatically protected by our Antiquities Act, which is pretty tricky. So that's it's less because it directly affects many kind of land use related processes. If we think that without any like confirmation from fieldwork that they should be treated really seriously. So for the meantime, we have decided that those are not like automatically protected for now. We might decide otherwise later. And one of the other things we have to like do is to like recognize this kind of remote sensing based assessment of archaeological sites as a standalone method by its own right. And the problem is that for now, the thinking in Finland is really much based on traditional archaeological fieldwork, so that the archaeologist has to go to the actual sites and observe it by himself or herself. And this is something different, so that this is basically just like one can sit comfortably in his own office and just identify new archaeological sites there. And also we have to establish all the necessary guidelines and processes for actually reporting this kind of stuff to the Finnish Heritage Agency. And to actually accomplish these goals, we have decided to add some new categories to our national databases. So we have decided to add a new category of archaeological sites that's specifically meant to this kind of unconfirmed, remotely observed archaeological sites and features. And the main features about this thing is that it's not going to be automatically protected unless the heritage management officials decide otherwise on case-by-case basis. And it's going to be implemented later this year. And here you can read the actual description of what this kind of new category is going to contain. So it's not really specific for AI in any way. So we decided to focus more on the remote sensing aspect and make this like useful in wider range of different scenarios. And the other part of this is a similar like description for this kind of remote sensing based archaeological research in like producing new data of new archaeological sites and also the existing ones. So we have recognized this as a standalone method in our systems. And this is also going to be implemented later this year. And here we are also like consciously downplay the AI part and focus on the remote sensing. So it's in our perspective it's pretty much the same thing whether someone does it by like himself or if they use a computer to aid them. All right, and the next question we have to discuss is the reliability of the data we want to integrate in our systems. And the key consideration there is actually in post-processing and validation of the data. So in these kinds of classification tasks or feature detection tasks, there are always bound to be some error in the results. And those errors can be classified into two broad categories. So we have false positives, so that the model, for example, identifies something as an archaeological site, but it's not. So it's like false result. And the flip side of that is the false negative, so that the model might fail to identify an archaeological site even though it exists. And like our approach to post-processing and like quality control of the data really depends on how important these two kinds of mistakes are to us, and like how much resources we have to like pour in validating the results, and also like how good our model's performance is really. And the model's performance here isn't like that critical actually. So it basically just affects like how much resources we have to use in validating the data. And the figures here, those might be a bit small, so you can't probably see all the things that are going on. This is just an like example of how this problem might look like in the data. So this is an actual example of one of our research areas in the LIDARK project. And what this shows is like the distribution of all the detected features based on the probability estimation given by the model. And the red ones are false identifications, and the green ones are actual archaeological objects. And in the left, there's a huge mountain of red, which are features with lower probability values, and all the kind of real features are grouped mostly on the right, where the probability values are really high. And what we want to see in such a graph is actually so that a situation like this, so that we can just filter out most of the false identifications as easily as possible. For example, in this case, we might decide that we discard all features to the left from here and only like put more resources in validating the ones with highest probability values. And this is a really simple approach. This is basically like adjusting the sensitivity of the model after the identification. And the next step we can do to improve the quality of our data is some kind of desk-based validation, so that we can actually like check all the features we deem interesting in case-by-case basis using GIS and the original LiDAR data. And this can be really fast, actually. It doesn't take more than a couple of seconds per feature, so we can do this for quite a lot of features. And the nice thing about this kind of desk-based validation is that the results are much more easily relatable to humans, so that the quality of the data after this kind of validation process is very similar to human interpretation, and basically it is human interpretation after that point. And the most precise thing we can do to ascertain that the data is good is ground truthing, which is someone has to go to the exact location where the feature is and check that it actually is what we think it should be. And this is quite slow and expensive, so we aim to do as little of that as possible usually. But the data would be comparable to more traditional archaeological surveys. So it has its place, and we've done some of that to just kind of check that our desk-based validation is good enough. And as kind of guidelines for doing this in the future, we have decided to stress this kind of desk-based validation, for we think that that's the kind of optimal level of confidence that can be achieved relatively easily. So we can require people doing this kind of research that they should do at least this before they send the data to us, and then we can add it to our Formenes-registret. And we have decided to require some kind of ground truthing or equivalent before we consider those sites as protected. And we can discuss that a little bit further with the next slide, which is our priorities and evaluations related to managing this kind of archaeological heritage. So this kind of methodology kind of puts us in a really interesting place. So it makes us really good at finding new stuff. And then after this, we have to come up with some way to manage the number of sites we find. And during our pilot project, it became obvious that we can't just continue business as usual, because we started finding so many things. And this pie diagram here kind of illustrates the situation quite well. So the blue slice represents the kind of known archaeological sites that are protected by our current Antiquities Act. The orange one shows the other kind of archaeological sites we have in our systems now that we think are interesting, but they are not protected by the Antiquities Act at the moment. And the green one represents the data from our pilot project, which is quite large compared to the existing data. So this kind of shows that any decision we make about how we are going to manage this new data has huge implications, especially locally. For example, this new data might not impact some of the regional museums that much, but some of those might be very much impacted. So we have to be quite careful. And at the moment, we don't really have any decisive answers to what we're going to do. And yeah, this is something we have to solve in the future. And to wrap it up, I will just want to say that yes, this has been a really good experience for us, so that the AI-assisted feature detection seems really useful, and we have found much value in it. And it does really enhance our knowledge of certain types of archaeological heritage. And in order to actually benefit from it in heritage management sector, we kind of have to first normalize it so that we have all the necessary guidelines and things in place so that people can start using it more efficiently, and to integrate it to all our systems. We also have to make sure that the people doing that have the necessary competence in GIS and LiDAR. Those are really the most important things. The AI part isn't that necessary in our perspective. And yeah, that was pretty much it. And thanks for your attention. And if you want to like more, I included some links to our previous publications about the pilot project we had. And also keep an eye on our GitHub page. We are going to publish all the code we did in the pilot project in really short time, possibly today, if I manage to power up my work phone. And also bear in mind that the EAC, or European Archaeological Concilium, is going to publish their LiDAR guidelines later this year, and that's going to be a really important resource. Thanks.